Hello, Mr. Price here, and this is the 7th video on the January 2007 Mechanics 2 paper, and this is on circular motion. Let's take a look. So, we have a particle on a piece of string, and this particle is rotating around the table, and something that I really want to know very early on is there friction on this table? Okay, so I'm particularly looking out for that when doing this question or reading the question. So we have a lightly extensible string of length 0.8 meters, and it's attached to our fixed point A, and it lies on a smooth horizontal table. Okay, so there's no friction involved here. The other end of the string is attached to particle P, and we know its mass, and it moves in this horizontal circle on the table with a constant angular speed of 2 radians per second, and we know the angle that it makes to the horizontal vertical as well. And our first task is to find the tension in the string. Okay, now almost your bread and butter for the circular motion questions is to always draw your force diagram. In fact, you'll probably want to. So in this question, I'm just going to quickly copy down the diagram that we had. So we had 0.8 meter length. Okay, and this made an angle to the vertical of 30 degrees. This is spinning around here at 2 radians per second. And I've got particle P of 0.3 kilograms. Do I know the radius? I don't, but I can calculate it. You know what? I might as well do that now because I know I'm going to need it, even if it's not relevant for finding the tension yet. Okay, so using trigonometry, you have 0.8 and we have 30 degrees, so this should be 0.4 meters. Okay, so now let's zoom in on our particle P. So for part I, here's particle P. We have a tension. There is a reaction force from the table, and there is the weight, and there is an acceleration towards the centre of the circle. Okay, so resolving upwards. So no, we can't resolve upwards because we don't know the reaction force. Resolving to the right, we have T sine 30 degrees is equal to ma. Now we know the mass, we don't know the tension, we don't know the acceleration, but we can probably find it out because we know the angular velocity. So A equals omega squared r. And it turns out we didn't need the radius, so substituting this in here, we get T sine 30 equals 0.3 lots of 2 squared times 0.4. So solving this, you should find a tension of 0.96 newtons. And that's part 1. Part 2, we want to calculate the normal force between the particle and the table, the normal reaction force. This should be quite a doddle. We know the tension on our force diagram, we know mg, we know T, we've got one missing force, easy. So, resolving upwards, we have the reaction plus T cosine 30 will equal the weight 0.3 g. You know the tension, so solve that, you get a reaction force of 2.11 newtons. Okay, part 3. Our particle now moves with a constant speed v meters per second and is on the point of leaving the surface of the table. Calculate the velocity. Okay, so we've got to ignore this angular velocity now because that's going to have changed. But a key thing to note is if it's at the point of leaving the surface of the table, there's going to be no more reaction force. Okay, that table is doing nothing to support that particle. So let's do a new force diagram. So now we have this situation. So our tension 0.3 g, and we have a new acceleration like so. Okay. So resolving upwards, or sum of forces up equals sum of forces down, because it's in equilibrium in this plane. So t cosine 30 equals 0.3 g. So our tension here is 3.39 newtons. Okay, and now resolving to the right, we have 3.39 sine 30 will be equal to ma. Okay, and we know that the acceleration in terms of the velocity is v squared over r. So 3.39 sine 30 equals 0.3 v squared all over the radius 0.4. So this will eventually leave us with a velocity of 1.50. Sorry, you couldn't see any of that. I'm really sorry. 1.50 meters per second. Okay. I hope you didn't miss too much of that. I might just have to review the video and make sure everything with that, all of that is okay. I'll just go through that again just in case. So I drew my force diagram. Resolving up, t cosine 30 equals 0.3 g, because it's in equilibrium in this plane. So that gave us that value. I resolved to the right, and there's an acceleration, so this resultant force in this direction is equal to ma. Substituting that in, you get that value. Sorry about that. And that's question 7 finished. Thank you.